time slots. At least this way they get a chance to listen to what I'm talking about. So like I said, welcome. Let me change the screen and maybe show that. So this is what I'm going to do is I'm going to introduce myself and the course a little bit, and then we'll talk about some of the red tape. Once we've got all that out of the way, then I'll watch I'll display the videos on YouTube in the week 1 playlist. And if you want me to stop at any stage, just let me know. I'll try and watch the text channels appropriately. And I know I can see some people are coming in now, and I might have to occasionally go and add them to the CET236 group so they can see the 3 text channels. Before I start, does anybody have any questions?
Yeah, I see that you have like a draft syllabus on Blackboard. Is there another one that you are going to go here or repost or whatever?
Right, so that's one of the pieces of red tape that I'm going to go through. One issue I found, I didn't realise we weren't supposed to be meeting on July 5th. So there's I think the schedule that I put in the syllabus on Blackboard has July 5th. I mainly make it draft until after the first meeting of the year, so that in case somebody has a question or points out an error or what have you. Once we've finished tonight's session, I'll make it the official one. I'm not saying that there aren't any errors in it after I make the official one, but at least that way it's no longer just draft. Okay?
Yep. No problem. Thank you.
You're welcome. Okay, so let's see if we can. So that's me. My name's Peter Katsoukis. I have degrees in electrical engineering and systems engineering. It's mainly control systems. If you wouldn't mind muting so we don't get the feedback that I could hear. Please use my CCSU email address if you need to contact me. This is supposed to be a completely asynchronous course, but like I said, I think some people prefer something on their calendar, so I'm putting this time on your calendars. If you don't need that, don't need to come to these sessions, that's okay, but usually everybody needs to talk to me at some stage during the semester, so please use that booking office hours link. What you'll see is it'll come here, and at the moment there's only a single reason for talking to me. It's general consultation. Later on you'll see I'll add another one, which will be the midterm, because I need you to book a time with me to take your midterms. I do all midterms orally, so you need to get on my calendar and we talk on Discord about the content of the midterm. But I'll talk more about that as we get closer to it. And then you select an appropriate date. At the moment I've basically put afternoons and evenings Tuesday through Thursday every week. If those don't suit some people, I'm happy to make other times as well. But I'll leave it at those times. Basically goes from 3 o'clock until 8:30. Hey, Michael, would you mind muting? You're
sorry.
It's okay. And yeah, so that's that piece. Let's go back here. And as far as I'm aware, we have a variety of program students here. We have mechanical engineering, we have mechanical engineering technology, we have manufacturing engineering technology, we have computer engineering technology, we have robotics, mechatronics engineering technology, and we have a student from UConn as well. So welcome everyone. If I've left any of your programs out, please let me know. But I think that's what Banner was telling me. So this is the updated schedule. I warn you, the summer session is a little accelerated compared with the usual fall or spring semesters. So there's time to do it, but you don't want to dawdle. Okay. The session today is basically setting the groundwork. There's some basic unit information, basic physics, Ohm's law, how to get power, that sort of thing, and then some basic material properties. Actually, let me move on. So that is the topic list. The items down in the bottom right that are grayed out and italicized. Unfortunately, we won't be doing an in-person lab. And one of the things you should have been able to get out of this course is being able to use a multimeter, being able to use a power supply, being able to use a function generator, and being able to use an oscilloscope. Now, we can't do those. What we can do is use a thing called LT Spice, which is a simulator that's freely available. You can install it on your machines, or you can use it on the CCSU app server, and I'll show you that shortly. In fact, before COVID, before we went remote, I didn't use LT Spice at all. And now that we're going back to in-person labs, I'm going to keep using LT Spice because I think it's a nice addition to the lab component for this course. It means you can prepare for the lab and know what to expect in the lab by simulating it before you get there. So that's kind of interesting. There is no required textbook for this course. However, if you do need support outside of the notes that I make available and at other online places, the textbook is the place I'm getting all of my information. So the notation and the wording and everything is straight out of this textbook. So please, if you do need support, the textbook is the place to go after talking to me about it. The clouds on each of these boxes is a chapter in the textbook, and the clouds indicate some of the chapters that I don't really use in the textbook. So you can see there's a few of them. We don't talk about Laplace transforms. We don't talk about Fourier series or Fourier transforms. We don't talk about frequency response. That's the textbook, Dorf and Svoboda, Introduction to Electric Circuits. And I'm not sure, I think I've got the 9th edition, but just about any edition should be fine. As I said, there are no formal classes in this course. I'm happy to talk to you about anything, either during those general consultation hours or during this slot on a Monday evening. Mostly what I'm going to be doing in this slot is playing the videos and maybe stopping them or giving added commentary over the top of the video. So let's have a look. What do you have to do in order to get this course done? You've got to do some labs, and they're all done using LT Spice. The first lab is basically just to show me that you have LT Spice installed or that you have access to LT Spice. While I'm here on that, let's just quickly go to apps.ccsu.edu. I think that's the URL, right? And I will go there, go to the Citrix gateway, and there's lots of things you can do from the app server. The particular thing I will need you to do is to go to desktops and go to engineering, science and technology desktop and open it. And it'll either, if you use the light version, it'll open in the browser. If you have the Citrix client like I do, it'll open in a separate window. And let's see what happens. Okay, so the labs are available from 6 a.m. until midnight, so don't try and pull an all-nighter. And on the desktop here there is LT Spice. Okay, and the first time you run it, it'll probably have to do some of this preparation step, but once you've done that, you don't have to update. You probably won't have permission to update. And that's LT Spice. One way to run all the labs is just run them here on the Citrix server. The other way is you can install it on your own machine, right? So it's available for both Windows and Mac OS installations. If I can see where it is, there it is there, right? So it's now starting up, I believe. There it is. Oops, where'd it go? And I'll open a recent file. Okay, and there's the version on Mac OS, right? They look a little different. The Windows version has lots of icons which makes things a little bit easier. The Mac OS version, you've got to right click to get all of the functionality, but it's all there. That's the labs. You will see, if you go, all of the assessment is available in Blackboard under the assessment tab, and I've put it all in Blackboard so you know when it's due, and it's all available from now until the end of semester. Okay, so actually let's just go back to the labs. For the labs, what I want you to do is, there is this Excel spreadsheet that has that I want you to use. It's a template for running for writing labs that I want you to use, and it's pretty simple, but I've found that it's better than using Word or something else, because obviously Excel lets you do calculations, and even though the calculations we need to do are pretty simple, this this spreadsheet. Now it's a bit small, so let me just zoom things up a bit. It's got all of the stuff that you should put in a lab report, right? The date, your name. I'm okay with you working with one other person on the lab, so put your lab partner's name there. The title of the lab, the objective, all the lab sheets have objectives. Each lab is different, so I'm not going to put exactly what the data is. And then the conclusions. And then whereas in the lab physically we'd have the different model names and serial numbers for the equipment, the main thing you'll put under equipment for these labs will be LT Spice. Okay, so they're all there. You will see also in Blackboard, as well as assessment, there's also this thing called assessment calendar. And I highly recommend you use it to see when everything is due. Okay, today is the 7th, and the first homework and the first lab are due at 11:59 p.m. on Monday next week, right, on the 14th. And then you can see we have stuff due all the way through. And then I've also got the oral midterm and the oral final. Like I said, it's a little bit jam-packed compared with the normal 13-week semester, but it's doable, and I'm okay with rescheduling things. I just don't want to reschedule everything. The other thing you should note about Blackboard is if you scroll down to the bottom here, there's this link that says get external calendar link, right? And you can use that and add it to the your calendar app, and it will show you when things are due in your calendar on your phone or on your laptop. I think I have that set up for me. Let's just see if I do. And it's particularly useful because if all your professors use Blackboard to set due dates, they're all there automatically. So it works out. I think it works out pretty nicely. So let's just see what the calendar looks like. And apparently I don't have it set up in my calendar, but what I should be able to do I've forgotten how to do it. But there is a way. It shows up on my mobile, so I'm not quite sure. Anyway, you can see it. You can see the calendar by going into Blackboard, and I suggest you use that link to add it to your calendar. Okay, let's go. So that was I talked about LT Spice. Web work. I collate all the grades for the course in Blackboard, but the the actual homework assignments are to be done in WebWork, and the URL is there. Right, so the first one is the fundamentals, and basically you go in here and you click on the problem, and it'll give you some randomized numbers. Each one of you will get a different set of randomized numbers, and you've got to answer the question. Okay, and you can check your answers, right? And if it's correct, it'll go green like that, and if it's not correct, it'll go red like that. Sometimes, if you leave off the units, it'll go yellow and it'll say that it was expecting units in the box. Okay. You can do that as many times as you like. There is no limit to the number of times you can check your answer in WebWork. What I see is what I will be doing, and you don't have to. If you're happy with your attempt at a particular homework set, it's okay for you to go into Blackboard, go to homework, click on the link and say, I'm done. Right? And if you want to upload your working, that's good. Particularly if you haven't got 100% on WebWork. If you upload your working, gives me a chance to give you feedback on what's wrong. Okay? But if you get 100% on WebWork, you obviously know what you're doing. So just saying I'm done is sufficient. You don't have to do that submission, right? Once the due date passes, June 14th, I will look at, probably on June 15th, I will look at the grades on WebWork, and right, I can go to student progress and I can click on fundamentals, and it'll tell me what all your grades are. Okay, and I'll transfer, well, I'll probably turn those numbers into a percentage and transfer that number into the column on Blackboard. You don't have to submit on Blackboard. Like I said, if you want to, that's okay.
Do we use our school login to get into this? I don't see a way to create an account.
No. So if you go to, there's two places to find out how to get there, how to get in. One of them is, I sent a few emails and I finally got all of the information into the email. So this green text down the bottom, your login name is the first 4 letters of your last name, and your password is the first 4 letters of your last name concatenated with the last 4 digits of your student ID. Okay, so for example, my last name is Koutsoukis, so in this example, my login would be Koot, K-O-O-T, and if my student ID was 12345678990, then my password would be KOOT 7890. Okay. I don't have access to the single sign-on for CCSU, so I've just set them up that way. What else? think that's about all I wanted to say with web work. I've found that talking to other students, or at least interacting with other students about the work, helps you understand. So what I'm doing this summer semester is I'm asking you to to try the tutorials. And there's one tutorial available at the moment, and it's going to close on June 14th. The only assessment for these tutorials is participation. And there's two components to participation. One of them is submitting answers to the tutorial questions. And the other one is reviewing answers of your classmates, two of your classmates. Right, so what if you go to tutorials in Blackboard, the tutorial sheet which with all the questions is there, and the idea is that you go to here and you view and complete, and you don't have to answer all of the questions on the tutorial sheet, right? I'm asking you to answer one question about charge, and it doesn't have to be the first one question about resistance from shape, one question about resistance change with temperature. I've set these linear algebra questions up. I'd like you don't have to do all of these. It's okay to just do one example of either solving the equations using elimination or substitution or a calculator or MATLAB. And then there's a few complex numbers questions, and then there's 3 series parallel resistor questions. It doesn't matter if you get it all wrong. The main aim is that you attempt them and that you look at other people's attempts. So once this submission time is over, June 14th, then you will be assigned 2 other people's tutorials to review, and I've asked you to grade those other. Again, you don't get docked marks for getting things wrong in these tutorials.
Is it like more like practice and participation?
Exactly. It's practice and participation. That's what I'm after in the tutorials. Not in the homework. The homework, you will lose marks if you get stuff wrong, but you've got plenty of chances to try and get it right. Here,
the syllabus, and it was 10% out of the course.
Yeah.
I figured it would be like participation or whatever.
Yeah, it is. That's it. That's it. It's participation. I want you to do it because I think it'll help you learn the material, right? The fact that you get it right or wrong is, for the tutorial, is neither here nor there. The aim is to try it. Okay, so that's that. And as it's
how is it determined whose work we're grading?
It just randomly chooses 2 other people's work.
Okay.
Okay. I don't think I haven't seen any way I can influence it at all, so I think it's just completely random.
How many chances do we have to submit like a correct answer on the home?
On the homework, so web work, as many times as it takes you to get it right. Okay, but once the due date is up, June 14th, 11:59 p.m, that's the grade you're going to get. I'll look in, if you haven't submitted your answers or your mark into Blackboard, I will go into web work and transfer whatever the number is from that
Gotcha.
page. Okay, so
Regarding the homework, Let's say if I do more attempts, although I got it right to practice, because it generates different numbers, you still pick up the best answer or the best score, right?
So I only, as far as web work is concerned, I only see the last score. So
Oh, so the last one has to be correct in order. I see what he's.
yeah, yeah. I don't think I can see the any history of your scores. So the only thing I see is what's on this page.
Oh, gotcha.
Okay.
Okay.
And that's homework tutorials. So I do exams differently from a lot of people. Two main things I do differently. I've already mentioned one of them. One of them is I do them orally. You have to explain to me how you would solve the question while we're on a one-to-one Discord chat. You'll notice in this server there are two chat channels, or voice channels. There's the one we're in now, the classroom, and there's the consultation, which only allows two people in it, me and somebody else.
Quick question.
Yep.
We have a midterm next week or this week?
No, I forgot. When's the when did the calendar say? I will send out more information once I've prepared it, but I'll explain what I mean. So the midterm at the moment, I would like everybody to have done it by July 10th. Okay?
Okay.
And what I'll...
Would there be any review for the midterm?
Sure, I'm happy. So let me explain the second part of what I do differently from other people as far as exams are concerned. I might not quite get there for this semester, but for most semesters, I release the exam paper 2 weeks before you have to do the exam. Right? So you have exactly what you have to answer. And the thing I had up on this is an example of what last semester's midterm was about. Right? I give topics. In this case, our midterm will have topics of charge, resistivity, resistance versus temperature, mesh analysis, and nodal analysis. And I will give you a number of example questions. Right? In charge, there's 3 in this paper. In resistivity, there's 4. In resistance versus temperature, there's 3. In mesh analysis, there's 2. And in nodal analysis, there's 2. And these are the questions I will ask you to answer while we're on the call. Not these ones. I'm going to redo them a little bit for ours, but this is what last semester's students were given 2 weeks before their exam. And
So it's basically like a take home, but you got to be prepared for it.
exactly.
Okay.
And the other thing is, I'm only going to ask you to answer one question per topic. Right? So I'm not going to, in this case, there are 14 questions, right? 10 on this page and 4 on this page.
So basically, we're getting the same question probably in different numbers.
Right, sometimes, like you can see some of these, I don't actually give numbers. The way I do the midterm is, while we're on Discord, I want you to explain your approach to the problem and how you would solve it. And then offline, I'll give you numbers for X, Y, Z, whatever it is, whatever the...
And is the offline part timed, or is like a day we have to submit it?
I prefer you to submit it on the day of your exam, but if you have the exam at, I don't know, 8:30 p.m. at night and you want to leave it until the next morning, I am okay with that. Right?
Another quick question to you. For the Discord part, how we have to explain it, will that be timed as well? Or is it whenever...
I don't time it.
How does that work?
I don't time it, but I've found that for these questions, most students take about 10 minutes. Some of them take a little longer. Some of them take shorter. I think the shortest midterm exam was with one of the best students, and he took 5 minutes.
This is my first time doing like all oral midterm and final. Is it like we're more using our critical thinking of how we would approach the problem, and then afterwards we do the problem and then send the work to you?
So what? Yeah. So what we're going to do in this course is I will give you approaches to how to solve each of these sorts of problems, and I want you to explain that approach, each approach, back to me, how you would do it. Right? I find that that process questions like that tells me more about how you understand the problem than the numerical solutions that we often do. I'll get you to do numerical solutions too, because that's important to get right too. But for me, the most important piece is understanding how to solve it. Okay?
So you give us a problem, and we just have to be like, all right, we take the two calculations of the two resistors, add them together, and then get how do you you want to calculate or explain the overall picture of the problem and how to get the answer, or you want the exact calculation?
So I'm not going to give you any numbers for the explanation. So you don't have to be exact while we're on Discord. Once we're off Discord, I will give you numbers, and then you have to be precise. But
It's like more of a knowledge test.
well, you can have your notes with you, but I find if you have to rely too heavily on your notes, it's going to take a lot longer, and you're not going to get it right usually.
Yeah, it will limit you basically.
Yeah.
Yeah, I see.
So anyway, I'll give you a bit more detail once I make the paper available, probably in about 2 weeks' time.
Okay.
Okay.
And class is every Monday as well.
If you want to, you like I said, this course was timed to be completely asynchronous. I find that some students prefer to have at least a little bit of connectivity with the professor. So that's why I've set these times up. You don't have to come to them. I'm not going to take attendance or anything like that. If you do want to talk outside of these times, just go to that booking page and book a time on my calendar.
Gotcha.
Okay? And
how long do you normally host these classes?
I'll be doing these every Monday evening except July 5th.
Okay.
Okay?
So what time?
6 p.m. to maybe until 9 p.m. at most. Maybe we might not take that long, but if I'm happy to spend that amount of time. I warn you though, I can't talk for an hour, more than about an hour. So I tend to take breaks every hour. So a break at 7 p.m. and a break at 8 p.m. if we're still going by then. Okay. And then the final is similar, but more complicated problems. And again, this is just the final from last semester. I'm going to rejig it for this semester, but it won't be too different. Okay, everybody happy with that? So, I haven't tried this before, so I'm going to just play the playlist, right? And I'm going to put the playlist into sorry, I just noticed somebody else joined. Oh, a few people joined. Let me add add them to the roles. Okay, and then so the week 1 playlist is what I'm going to start playing shortly. And I just put the link to this in case you're into the Materials 236 channel. So unless anybody has any other questions, actually, I did want to quickly review. Sorry, I forgot about that. Just for your other information, the course syllabus is there in Blackboard. It is a draft, as we noted earlier, and I don't think I got around. Yeah, see, I forgot we weren't going to be meeting I think that's the wrong date. We weren't going to be meeting the day after Independence Day, so I have to change that. But everything else in here should be pretty much right. There's the link for the bookings in there, right? So that's all there. And then the other piece is under Tools for Remote Work. There's again the link for the bookings. There's the lecture, the full playlist for all topic videos. There's a link to this Discord server. There's a link to WebWork. I use OneNote to take notes, right? I probably won't use it much here, but it's a good way of sharing stuff. So if you have OneNote, let me just show it to you. I've added a few bits and pieces to it that might be of interest. I work pretty closely with another professor at Central called Professor David Broderick, and Professor Broderick has taught this course quite a bit, and he's written or has a draft version of a textbook. So some of what I've presented is from Professor Broderick's textbook. The textbook's also available.
So we don't have to buy the book?
You don't have to. It shouldn't be necessary. However, if you need extra support, I'm taking all of my notation from that book, so it's another resource for you to use to help you get through the course. Okay. This is another one. This is a PDF from Professor Broderick that I've helped write, and then there's a 2-page crib sheet that I used to use when we used closed book exams and allowed a single page, double-sided page of notes. If you need to share stuff with me, what we'll do when I do the exams is I will add your particular exam paper under your name in this OneNote notebook, and I will write on it as we do the exam and give you feedback. There's a link to where to get the LT Spice simulator here as well. And if you need to scan to PDF, Adobe has a nice app for your phone that generates nice PDFs rather than having to scan it in a flatbed scanner or something. And that's about all I wanted to say. Sorry about that. Okay, so we're ready to start watching the introduction. So there's 3 videos. There's the basic concepts one. There's the series parallel resistors and Kirchhoff's current law and Kirchhoff's voltage law, and also dividers. And then there's some background material on linear algebra and complex numbers. So I'm just going to play them in that order. I'll probably, if you want me to stop and explain anything, I'm happy to do that. I'll stop the video and we can talk about it. Yeah,
Comment.
yeah, go for it.
So to kind of reiterate the whole book thing, if we choose not to buy the book and we reference the Broderick's resource here, would that be beneficial as well, or would it be more beneficial to reference the extra work in the actual book? I understand that you use the examples from the text, the other text, but
Right. I find Professor Broderick's way of writing easier to understand than the textbook. I think the textbook's a little stilted. Professor Broderick tends to do things a little bit more laid back. Not too laid back. Like, you've got to be a bit precise with this stuff. But I tend to prefer his way of presentation. Okay.
yeah, that's fine, because I also use OneNote like you, and I would prefer to have like screen grabs or whatever of examples and stuff. So
Yep. So what I
use it.
yeah, what I haven't done is let me do that now. I usually put so I've put under lecture notes in OneNote all of the topic notes that I use for all of the topics we're covering in the semester. They're already there. And then what I usually do, and I haven't done, let me do that now, is I usually export the slides I use tonight into PDF format. And I think I've... Okay, and we'll kill that. And then I usually... let's put it there and say add page, and week 1 watch party, right? And we'll put that up the top, maybe, if it'll let me. Right, and then I can insert those pictures, or that printout, that PDF of the slides that I put up on the screen just now. So that takes a while to sync up, but it's usually reasonably quick, and they're the slides that I used this evening. Okay. Okay, so let's unless there are any other questions, let's get started. And what I might do... Go ahead.
I posted a link to the textbook in the new students chat text channel.
Ah, okay. Fair enough. I'm not going to do that, but that's all right. You did. Okay. So let's get started. And just let me know if you can hear the audio for this. I don't know. I haven't quite done that. And I'm going to turn my head off. So.
Okay, this is the first video with some actual course content in it for CET236 circuit analysis, and I'm recording this in the summer for the summer of 2019.
Yeah, so even though these are videos are a couple of years old, the content actually hasn't changed. I did this course as an undergraduate in... I'm going to have to think about it, but I think it was 1984. So this stuff hasn't changed much since then. The presentation and having simulators and all that sort of stuff has. But even back then I had a little bit of a simulator. So sorry about that. Let's keep going.
Team session. So what do we have to get through? We have to get through this list. And we're currently at week 1, and this session, this topic is about basic concepts. So resistance, power, energy. We'll take a break, and this session will also talk about series, parallel, and combination circuits, but that will be in a separate video. You'll notice that all of these notes and the videos are split up by topic rather than by week number, so that's why there's we'll probably cover a couple of topics in each non-lab week. So here we go. This topic is about voltage, current, resistance, power, and energy. So we need to think about the voltage in volts, which has a unit of capital, or is denoted capital V. We have current, which has units of amps, which is denoted capital A. The letter for the variable we usually use for current is the letter I. The letter we use for voltage is the letter V. And then resistance lets us use Ohm's law to relate voltage and current. So V equals IR. So R is the resistance. Resistance is measured in ohms. And the unit, or the way we denote ohms, is as a capital Greek letter omega. Power is related to, is given by the product of the voltage and the current, instantaneous voltage and the current. And then the energy is going to be the integral of the power over time. So let's quickly go through some other pieces we need to know about. Right, so...
Okay, so let's just quickly go through that. In fact, let me just scroll down here. Right, so we talked about, or I talked about voltage, current, and resistance, and the relationship between them, V equals IR. Right? The voltage is measured in volts, the current is measured in amps, and the resistance is measured in ohms.
This course uses SI units. It does not use imperial units or US units. So we're talking meters, kilograms. We'll be using temperatures in Kelvin or Celsius, and there are the other units that we'll be using. You can see there's power, which has a unit of watts or joules per second, which has a symbol W. Another thing I didn't talk about is we're going to talk about, when we talk about current, current is really measuring charge per second. So we need to have a look at the unit of electric charge, which is the coulomb, and its symbol is capital C. Anyway, have a look through that. Apart from the basic units in this table, we also need to understand the scale of the multipliers, ranging all the way from tera at 10 to the 12th or femto at 10 to the minus 15. The ones we'll generally tend to use are kilo or K for 10 to the 3, milli for 10 to the minus 3, micro for 10 to the minus 6 nano for 10 to the minus 9, and pico for 10 to the minus 12. And they have symbols of small k, small c, small m, Greek letter mu, small n, and small p. Make sure you know those. Okay, so here's the basic unit of current. As I said, the charge is the integral of the current with respect to time. So that means the current is the derivative of the charge with respect to time. I don't have a similar slide for voltage, but just to remember, it's capital V is the symbol to use. And then the power is the rate of change of energy with respect to time. So it's dW dt, which is dW dq times dq dt, which is V times I. So the voltage times the current. We're also going to be using Ohm's law, which is V equals IR, or here V equals RI. V is the voltage, R is the resistance in ohms, and I is the current in amps. The voltage is in volts. When you have a piece of material and...
Yeah, Professor, I think you're muted.
Yep, I am. I wasn't saying anything, so that was okay. I was tempted to say something, but I decided against it. Okay? Oh, was that muting everything that was coming from my machine, was it?
Yes, we couldn't even hear the video. That's the thing.
Okay, sorry. Okay, my mistake. So should I go back and review it?
Probably.
Okay, sorry about that. I was just chugging on my tea, and I didn't want you to hear my swallowing sounds. But anyway, sorry about that.
joules per second.
Let's try that again.
It uses SI units. It does not use imperial units or US units. So we're talking meters, kilograms. We'll be using temperatures in Kelvin or Celsius, and there are the other units that we'll be using. You can see there's power, which has a unit of watts or joules per second, which has a symbol W. Another thing I didn't talk about is we're going to talk about, when we talk about current, current is really measuring charge per second. So we need to have a look at the unit of electric charge, which is the coulomb, and its symbol is capital C. Anyway, have a look through that. Apart from the basic units in this table, we also need to understand the scale of the multipliers, ranging all the way from tera at 10 to the 12th, or femto at 10 to the minus 15. The ones we'll generally tend to use are kilo or K for 10 to the 3, milli for 10 to the minus 3, micro for 10 to the minus 6, nano for 10 to the minus 9, and pico for 10 to the minus 12. And they have symbols of small k, small c, small m, Greek letter mu, small n, and small p. Make sure you know those. Okay, so here's the basic unit of current. as I said, the charge is the integral of the current with respect to time. So that means the current is the derivative of the charge with respect to time. I don't have a similar slide for voltage, but just to remember, it's capital V is the symbol to use. And then the power is the rate of change of energy with respect to time. So it's dW dt, which is dW dq times dq dt, which is V times I. So the voltage times the current. We're also going to be using Ohm's law, which is V equals IR, or V equals RI. V is the voltage, R is the resistance in ohms, and I is the current in amps. The voltage is in volts. When you have a piece of material and you want to figure out what its resistance is, then you can get that from a thing called the resistivity and the physical dimensions of whatever the thing is. So here we have a cylinder of length L and a cross-sectional area of the cylinder of A, capital A. The cylinder is made of a material with a property of the resistivity property, which is measured in ohm meters, and the total resistance of that piece of material, R, is rho times L on A. Okay, so rho is ohm meters times L, which is meters again, so the numerator has units of ohm meters squared. Area is in meters squared, so if we divide by meters squared, that means we end up with our omega, or ohms, as the unit. Another
Okay, I just wanted to quickly talk about a dinosaur. This is a model of an Apatosaurus, and you may think, what is he doing? Well, that resistivity, you could think about trying to figure out what the resistance of this Apatosaurus model is, right? And the way you might go about doing it, and OneNote always does strangeness for me. The way you might go about doing it, right, and I'm going to draw a really terrible version of the Apatosaurus here, right? You've got the head, and you've got the tail, and maybe you've got some legs, right? But what you could do, let me just go back to the other view so you can see what I'm drawing. That might be better. Right, what you could do is you could say, well, let's approximate the head and the neck with a cylinder, just like the one that was in the video, and then use a bigger cylinder to approximate the body. And it's only an approximation, it's not exact, but then you could use yet another cylinder to get the tail. And if this is section 1 and this is section 2 and this is section 3, then you could find, assuming these are all made of the same material, so rho doesn't change, but you could find the resistance of section 1 by saying R1 equals rho times L1 on A1, R2 equals rho L2 on A2, and R3 is equal to rho L3 on A3. And the total, which we actually don't know how to do yet, but the total, you'll have to believe me, is just the sum of those three resistances. But it doesn't matter what the shape is, right? You could, provided you can find the length, provided you can find the area, and provided you know the material that the thing is made out of, you can calculate or approximate what the resistance is. Okay, so that's resistivity. The next section is about how resistance changes with temperature. And I'll go back to that.
Property of resistive materials is that their resistance often changes with temperature. So this expression at the top of your screen shows the relationship between the reference resistance, Rref, and the current resistance, R, given that the reference resistance was measured at the reference temperature, Tref, and we're now measuring the resistance at current temperature, capital T. The relationship, the number that's specified by the type of material, because each material has a different value for this, is alpha, the temperature coefficient, which has units of 1 on degrees C. Note it's degrees C, not degrees Fahrenheit, degrees Celsius rather than degrees Fahrenheit. And here are some common materials and values for the resistivity and for the temperature coefficient for each of them. Probably the most interesting one is the carbon graphite line there, because a lot of the resistors we're going to be using are made up of carbon or graphite.
Yes, so these two pieces, the resistivity and the temperature coefficient, they're both properties of the material. So for our Apatosaurus, right, our dinosaur, I would suggest that the closest thing on this list is probably the one second from the bottom. It's this hard rubber. It's maybe not quite right, but if you used hard rubber. And note that on this table, some of these numbers, the carbon one, the germanium one, the glass, the silicon, and the hard rubber one, is not a single number. There's a range of values. The hard rubber ranges from 1 by 10 to the 13th to 100 by 10 to the 13th. Right? The glass one ranges from 1 by 10 to the 9 to 10,000 by 10 to the 9 depending on the type of glass.
Okay, a quick change in gears just to talk about the sorts of circuit elements we're going to be using in this course. So the top three there, the left one is a resistor. It has a current going through it and it has a voltage across it. The middle one is called a capacitor, and I'll get into more detail in a much later video about capacitors. The third one on the right is an inductor, and again we'll talk more in more detail about inductors in a later session. The other things to notice are the sources, the voltage and the current sources. The left one is what's called an independent current source. That is, it just has a value. In this case, it's putting out 2 milliamps. The next one, which is drawn as a diamond with an arrow in it. The first one was a circle with an arrow in it. Is what's called a dependent source. What it does will depend on another measurement somewhere else in the circuit. In this case, somewhere else in the circuit there is a definition of Vx, and the current that this source is putting out is 4 times Vx. Next we move on to current sources, and here we've got two representations. The leftmost one is the just showing a 12-volt battery, and that's the symbol that usually means a battery. A more generic representation is the one on the right, which is a circle with a plus and a minus in it, and it's still a constant voltage source, but it's not necessarily a battery. It could come from something else. Note that the positive on the battery representation is the large plate, so that's at the top of the VS battery, and note that the circle VS has the plus at the bottom, so those two have opposite polarities. The left one has the positive terminal at the top, the right one has the positive terminal at the bottom. Just like we have dependent current sources, we can also have a dependent voltage source, and that's what the diamond with the plus and the minus is representing. Here again we've got another voltage defined somewhere in the circuit called Vx, and the value that this source is putting out is 4 times Vx volts. Okay, they're the things we're going to be working with. And just a quick talk about polarity. So here we've got a device. It could be a resistor, a capacitor, or an inductor. So it's just drawn as a box. And we have I1 going in one way and I2 going in the other way. What this means is that I1, because it's going in the opposite direction of I2, means I1 equals minus I2. Similarly, if we have voltages measured with respect to different directions, so here VBA is measuring the voltage at B with respect to A, so that means that the A has the minus sign and the B has the plus sign. That's going to be the negative of VAB, which is the voltage at A with respect to B. Okay, so here VAB has the plus sign on the A and the minus sign on the B. And finally, for this topic, the passive sign convention. One of the first quizzes I'm going to get you to do is about the passive sign convention. Passive sign convention says that a passive device always has the current flowing into the positive terminal of the device. Right, so the left-hand item there has the current I flowing into A, and that means that this device does adhere to the passive sign convention, and that means it's a passive device, and the power received by that passive device is equal to VI. If we had it going the other way, so on the right hand diagram we have the current going into the negative terminal of the device. Now P still equals VI, but now the assumption is that this is an active device, so we're not receiving power into this device, we're producing power or supplying power out of this device. The passive sign convention is a very important thing to note, particularly when we get to mesh analysis. I suggest you have a read up on it, and I'll try and put some more notes in the in Blackboard about that. Okay, that's the end of this session, this topic. So let's move on to the next one.
Okay, so
So this is CET236, and
let's stop there for now. I'm going to have a brief break, probably about 10 minutes, but before I do, I will reiterate how important the passive sign convention is. The biggest, or rather the most common mistake that I make, and the most common mistake that students make in this course, is getting the sign wrong. And it's largely around this passive sign convention. Let's just parse those three words, right? Passive means that it does not apply to active devices. And active devices are things like batteries or power supplies, voltage sources or current sources. Okay. Passive devices, the passive devices that we will talk about in this course are resistors, capacitors, and inductors. Everything the passive sign convention holds for those three things. And as it said, and I'll draw it again, if you have a device and you say that the positive, so the voltage across the device is that, it goes from the negative side to the positive side, then so this is the voltage. The current flows into the positive side. Right? If that's true, then everything works, right? P equals VI, and just as importantly, V equals IR. Ohm's law applies. if your device does not satisfy the passive sign convention, then neither of those things are true. So you need to make sure it's satisfied. We've talked about passive. Sign just says which side of the device is the positive and which side of the device is the negative. The third word, convention. It is completely up to you to decide whether this device has the selected directions on the top device that I drew first, or whether it's that way round. Provided the passive sign convention holds, either of those two will work. It's up to you to choose the directions and which is the positive side of the device and which is the negative side. But you have to choose, and you can't change your mind halfway through, or you have to start again from scratch. Any questions so far? Okay, so I'm going to take a 10-minute break. When we come back, I'll quickly look at some of the homework problems related to those two questions, those two topics, resistivity and resistance change with temperature, and then we'll go on to the next videos. Let's go with the timer. Just like the... I'll be back when the timer runs out, I hope. Okay, so the two pieces that you should have got out of that are to do with resistivity. Resistance equals rho, the resistivity, times L, the length of the piece, divided by the area. And if you have a look at there's also the basic units, right? So here's an example of problem 1. A wire has a current of 30 microamps flowing through it. How long does it take for a charge of 45 coulombs to pass through the wire? Right, remember a single amp is 1 coulomb per second. So if we want 45 coulombs, then to get it in 1 second, we'd have to have 45 amps, but we've only got 30 microamps. So 30 by 10 to the minus 6 coulombs per second, and right, so 30 by 10 to the minus 6 should be 30, not 20 coulombs per second. And we want to find the number of seconds, so we've got 45 coulombs, so we probably want to divide 30 by 10 to the minus 6 into that, and we get 1.5 million seconds. And most web work assignments want answers need a unit. Sometimes you'll see the unit put outside the box, in which case you don't need to add a unit. If the question is asking for a formula, you probably don't need to add a unit, but if it's asking for a numerical value, you should put a unit in, right? And I can check my answer. I think I checked that one before. And I'm going to submit that one and then go to the next problem. Right, this one says a 6-volt lantern battery provides 1/4 of an amp to operate an electric bulb. How much energy does the bulb dissipate in 0.75 hours of operation? Your answer should be in joules. So energy in the SI unit scheme of things is in joules, and that means you need a capital J at the end of your answer. So remember, power is joules per second, so we need to find the power, which is P equals VI, so that's 6 times 0.25. Right, that gives us our 1.5, and that's watts, or 1.5 joules per second, but then this is happening over 0.75 hours. So how many seconds is that? That's the number of hours, that's the number of minutes, so multiplied by 60, and that's the number of seconds. So it should be 4050. Which is what I had. I think I already answered the first 3 questions. And if I submit that, it should give me the correct, and I can move on to the next question. An alkaline battery is rated at 165 amp hours. What is the maximum current it can supply for 15 hours? Right, so amp hours is one of these strange units that people tend to sell those USB power bricks in. They probably use milliamp hours, but amp hours is a bit of a strange unit. But anyway, we can still work with it. 165 amp hours and 15 hours, so we just do 165 and 15 gives us 11, and that looks like the answer that I had before. And how many days will it last if we're discharging at 1/4 of an amp? And in this one, the units are outside the box, so we don't have to put the units inside the box. So 165, now it's 1/4 of an amp, right? So it's that many amp hours. So it's that many hours. So the question was how many days? Well, there's 24 hours in a day, so that's 275. And I think again I had that one correct before. And now we've got to get a charge. So a 48 volt battery pack supplies 42 milliamps of current for 20 minutes. Calculate the charge. Right, so this time there's, for the first question, there's too many numbers, right? We've got 42 by 10 to the minus 3 coulombs per second, and we've got 20 by 60 seconds. So the total charge is going to be 42 by 10 to the minus 3. That's minus 3, right? That's the coulombs per second, and then we've got 20 times 60 second, 20 minutes and 60 seconds in a minute. And that's not right. I think I forgot to put an up arrow there. Right, so that's 50.4. And the unit is going to be coulombs, so the capital C. And then find the energy in watt hours that the battery delivers to the calculator. So watt hours. How many watts do we have? Well, we multiply 48 by 42, right? That's going to be our power. So we've got our 42 by 10 to the minus 3 and 48 volts. So it's 2.016 watts. 2.016 watts. And then how many hours was it? It was 1/3 of an hour. Right? So watt hours right, so it's 0.672, which seems like a little bit of an odd number. And again, the watt hours are outside the box, so I'm going to submit those, and it looks like we're good. Okay, then we've got a thing about the passive sign convention. Right, and remember we want to make sure that the current flow is going into the positive side, the positive voltage side. So for A, we've got 20 going into the positive side, so that's a passive device. Here on number B, we've got the current flowing out of the positive side, so that's an active device. For C, it's flowing into the negative, which is the same as flowing out of the positive, so that's also an active device. And here we've got 2 milliamps flowing out of the negative, so it's flowing into the positive, so that's a passive device. And then the question is, how much power is dissipated by element A? Well, P equals VI. V is 1. I is 0.02, 20 by 10 to the minus 3. So the power dissipated is 1 times 0.02, which is just 0.02. And the power unit is watts. and how much power is dissipated by element C. Now this is a trick question, right? Element C is providing power, so it's not dissipating, or it's doing the negative of dissipating power, right? So you want to have a look at so the power involved is still VI, but because it's an active device, VI 4 by 10 to the minus 3 times 5 is going to be 20 milliwatts generated or provided, not dissipated. So it's going to be minus 0.02 watts. And I think that's right. Let's just check I got it right. Yep, I get everything right. Okay, that's problem 5. And then problem 6. This looks like it's a oh, this is excuse me, this is again a power question. So resistors have power ratings, in this case 1.25 watts, and if you exceed the power rating of the resistor, then it'll burn up. So you don't want to exceed it, so that means you don't want to go over the voltage or whatever. So let's have a look. Determine the maximum voltage that can be safely applied to that. So we have, well, let's go back here, right? So what did we have? We've got 3K3 resistor and 1.25 watts. So R equals 3300 ohms, right? And P equals 1.25 watts. And we know that that equals V equals IR. Sorry, we know that power equals V times I. We also know that V equals IR, right? We know Ohm's law. So what you can do is you can rearrange that and say that I equals V on R. Right? So you can rewrite that power as P equals V squared on R. Right? So now we can say V squared on R equals P, or we can say V squared on 3300 equals 1.25, or V squared equals 3300 times 1.25, or V equals the square root of 3300 times 1.25. And let's see what so the square root of 3300 times 1.25. Right, it's about 64.2. And again, there's no unit, so I think we have to do that. Right, so there's that one.
That made me think of a question.
Go for it.
If there's no units for ohms, or if we have to enter units for ohms, do we literally type ohms, or is it?
Yeah, good question. Yeah, it's just I think OHM is enough, maybe OHMS, but I think OHM is enough.
But when you check your answer, it'll probably say like it's if it's not right, that it would be incorrect, then you could try like with an S or without.
That's correct. Yeah.
Okay.
Yeah. Yeah. Good question. I've come across that one before. So problem 7: a smartphone uses a battery that provides 4.8 volts and stores 4.8 watt hours of energy. How many minutes will the phone operate if it draws a constant 36 milliamps? Okay, so watt hours. So the total power is 4.8 times 36 by 10 to the minus 3. So 4.8 times 36 by 10 to the minus 3. Right? I think that's right. 4.8 times 36 by 10 to the minus 3. So that's the number of watts. And we've got 4.8 watt hours. So we want to get do we want to get hours? We want to get minutes. So to get hours, we divide just the what was it? 4.8 again? 4.8 watt hours. So we have 4.8 and we divide our watts into that, into watt hours to get hours, right? So it's 27.78 hours, but the question's asking minutes, so we got to multiply that number by 60. So 1,666, 67 maybe. So 1,667, and I'm not sure. Is it minutes? Yeah. So there we go. And that is all you have to do for the first homework. That should be relatively straightforward. I know at least one of you has completely finished it, and a couple of others are most of the way through it already. So have a look at that. Any questions?
Okay, so just up to, so what's due exactly for the 14th? The homework, the lab, and what else?
Good question. Let's have a look. So go to assessment calendar, and the two things that are due on here are the homework and the lab. And I would also like you to have made a submission in the tutorial questions as well, so that this one doesn't show up in the assessment calendar. I haven't figured out how to make it show up. Okay. But
Okay, thank you.
you're welcome.
And for the lab, are we doing it with partners?
If you want to, you don't have to, but only one partner. I don't want groups of 3, just groups of 2. If you
Okay, and there any tutorial for the lab, or it just should be straightforward?
The first one is basically just installing LT Spice, or being able to access LT Spice via the Citrix server. I think it's a good question. I thought I might have had.
So basically, if we know how to access it, we don't have to do anything for the first lab.
Well, you have to submit the first lab. Let's just have a look at the first lab, right? So the first lab does ask you to actually do something with it, right? So there's the lab sheet, right? And it doesn't show up, but this text here is actually a hyperlink to the Analog Devices download page if you want to install it yourself. So you've got to construct that circuit with this thing as being 10 volts R1 being 100 volts, R2 being 220, and R3 being 330. So let's see if we can do that. In fact, let me make a new schematic, and I'll kill that one. And I actually like, it won't let me scroll. I actually like setting it up beforehand, right? So one thing you can do is you can just use F3 and just say draw wires. So I usually prefer to just draw the outline of the circuit first, like that, and then I can I like adding the ground. You need to have a ground, that's this triangle thing indicated, right? And then again you need to draw a wire between the ground and the bottom of that. Then you need to insert a component, and I'm going to go with a voltage source first. Right, just type VO and plug it in there, and that'll add it. It doesn't look like a battery, but it's the same. This is a voltage source, and the voltage source has to be a 10-volt voltage source. So we'll just right click on it and give it a value of 10 volts. Right, so there's our V1, and then I need to add another component, and this time I want a resistor. Now the resistor comes out in that orientation. If you go Control R, it will rotate it for you. Right, so there's our first one. I'm going to put R2 there, and I'm going to put R3 there, and then I need to do another what was it, F3 to join up my resistor. Okay, so there's the circuit, and I need to right click, and R1 was supposed to be, what was it, 100 ohms. R2 is supposed to be 220 ohms, and R3 is supposed to be 330 ohms. Okay, so there's the circuit, and I want you to include a screenshot of this circuit, so just do something like that. You can do the similar thing in Windows. And then I need you to measure the voltages and the currents through each of the resistors. Now, the way you get the circuit to actually simulate is you hit the run button, but it's going to give me an error when I hit the run button, right? Because it says no analysis command found. So what you've got to do is you've got to give it a SPICE directive, and that tells LT SPICE what sort of an operation you want. And maybe the easiest is to just get the operating point .op1, and that'll come in as some text that you can put on the circuit, and then you run it, and then it comes up with a plot. The plot's empty because you haven't selected what to plot yet. So we can go back over here and we can get the currents. Now, if you look at this current, I've got the current source, or the current in R1 flowing from right to left. I don't like that. I want it flowing the other way. So what I'm going to do is I'm going to edit, if I can figure out how to do it, I'm going to edit R1. No, I'm going to cut it out. I'm going to try it again.
So before you get too much further,
Yep.
It doesn't appear to let me. I can add in the ground on this and like lines, but it's for whatever reason I can't add in like the resistors or thing like that. If like you click on it and it just keeps saying ready. Is there anything else you're supposed to do?
This is running under Windows,
Yeah, well, I'm using
the Citrix
that
server.
remote application server. Yeah.
Shouldn't be. Let me see if I.
I mean, I could close and reopen it if it's stuck or something.
Let's just see if I can run it again. I'll try doing it on. There are some slight differences between. So new schematic and is it F2, F3? Like I said, I prefer drawing it out first, and this time I'll also put R2 there, and then I'll put the ground on, then F3 again, and then component and voltage. So that just let me go over the voltage, go over the wire, and add.
Yeah, that could be it too, because so I try and do the same thing you just did to add the component, and I have no like library or anything.
Oh, you got no library.
Looks like there's nothing associated with.
Okay. I had that problem at one stage last semester, but it resolved itself. What you'll have to do is I'll have to see if I can upload the library to Blackboard, and you may have to leave it with me. I will try and resolve it.
Okay. Yeah, I see two different options. They're both pulling C users and then my username. Oh yeah, I could try and install it on my computer for now.
Yeah.
Use it that way.
Yeah. So you saw when I started it up, it had to install the library. Sometimes for whatever reason it doesn't do that, and I don't know why. But when I started it up for the first time, it did. So I'm not sure. But yeah, let me see if I can reproduce it. But I think what you've got to do is download the library, and then I've forgotten where the preferences are, but you can set it up to point to a different place in the library.
Yeah. I've had to do similar stuff with different applications, so I should be able to figure out with it right.
Yeah. Leave it with me. I will.
Hey, I closed it and reopened it, and it worked.
It worked? Okay.
I think so. What was the component? I could just type in resistor here.
Yeah, RES or VOL, one of those, and it should show up.
Yep.
You got it?
So it looks like closing it and reopening it.
Okay, thank you. Good to know.
Thank you.
Okay, and then you can just plug them in there, and like I said, you've got to. What I was doing over here is I didn't like the direction that the current was going in, so I'm going to select that if I can figure out how to.
Is it also possible to like extend, like if the symbols are coming out too big, can you extend the lines to make them, or is it you have to redraw it?
good question. I don't know an easy way to do it. Yeah. I usually just get used to the right scale of the thing, unfortunately.
Yep, no problem.
Okay. So that's going in the right direction now. That one's still going in the wrong direction. So let's cut that one out again. And then rotate it so that it's going in the right direction, and then putting that back in, and it's still going in the wrong direction. Let's try that again. Oh, I probably have to kill that and rerun it, maybe. That's the other thing. If you change the circuit, and it's still giving the same answer, you may have to stop the run again. So kill that run window. I think they just rotated it back again. That's no good. Doesn't matter. The only difference will be that the current will be oh, now it's going the right way. So that one's going that way, that's going that way, that one's going up, which is probably the wrong direction. That's why it's negative. And you want the voltage. So the other trick with this one is going to kill that. The other trick with getting the voltage across each of the resistors, because that's what the lab is asking for, is you want to make sure you know which side you're starting with. And I'm going to start on this side. You left click and then drag keep the button down and drag until the probe changes color to black. And then you'll get the voltage just across R1. Similarly, you can click and drag across R3 to get the voltage across R3. And the voltage at R2 is just there. You won't be able to drag, and well, you will, I suppose, but it'll give you the same as just measuring the voltage at that node. And then the other thing you can do is you can use Control L, or is it Control L? No, maybe it's Windows L. No. View the SPICE error log, and what that'll give you, I think it'll run automatically in under Windows, but you've got to bring it up yourself under macOS. And it'll give you the actual voltage, node voltages and device currents. It won't give you the voltages across each of the resistors. You'll have to use the graph here to pull those out. But at least the currents are available directly from that error log. Okay. That's lab 1. Wasn't quite intending to go quite that deep, but let's leave the lab there unless anybody's got any questions. Okay, so I'm going to go back to watching the next one, the series parallel KCL, KVL, and dividers video, which is about 15 minutes.
So this is CET236 and it's topic number 3, which is still in our first session. So what I need to talk about now are series circuits, parallel circuits, combination circuits. I need to talk about Kirchhoff's voltage law, Kirchhoff's current law, and voltage dividers and current dividers. So let's have a quick run through that. So I've already talked about voltage, current, power, energy, and I need to talk a little bit more about the next things on this topic list. So a series circuit is when you have two elements, in this case there's two resistors, and they're connected in series if they share one node exclusively. So here is our shared node, the connection between the two resistors here in the middle. There's nothing else connecting to it, so these two resistors are in series. When two...
Okay, so I probably should have introduced the idea of a node, right? So a node is very simply an area of constant voltage. Right, so if I have a resistor and another resistor like that, oftentimes I will draw a node like that as a dot, but that's not the node. The node is every part where the voltage is the same. So it's all the way along the wire from one end, from one component on the left hand side in this case to the other component on the right hand side. Okay, so that's what a node is, an area of constant voltage.
resistors are in series, we can redraw them as a single resistor and the resistances just add. So we get R1 plus R2. And the reason for that is because if you have a current coming through the resistor, it comes through R1 and then it goes through R2 as well. So current through R1 is the same as the current through R2. Okay, so that means the voltage drop across the resistor is just given by Ohm's law, IR1. The voltage drop across this resistor is given by IR2. So the voltage drop from this node to the other side of R2 is I times R1 plus R2. And so we can rewrite the two series resistors as a single resistor summing their resistances. That's series. Similar.
So I used that idea of series resistances when I was talking about the resistance of the Apatosaurus, right? In that example I had 3 different resistors, but those 3 resistors are all in series, and so the same current flows through each resistor, the neck, the body and the tail. So you just sum up the resistances just like we did for the 2 resistances in this video.
Well, the next thing on the list is parallel circuits. Here, 2 elements are in parallel when they're connected between the same 2 nodes. So here's a node and here's a node, and this resistor are connected between the same two nodes. And the thing that's equal here, whereas before with the series circuits we had the current being equal, now the voltage drop across them is equal. I'll briefly digress and talk about what I mean by a node, right? In this course, we're going to talk about a node being an area of constant voltage. So here, it just means this whole collection of wires, this wire and these two wires, consists of a single node, and then at the bottom, this wire and these two wires also consist of a single node. There's no voltage drop from here to here. There's no voltage drop from here to here. The voltage along all these wires is the same, so this is a single node. One thing you've got to be careful of with parallel circuits is that they may not be drawn as if they are in parallel. Right? For example, in this case, if we decide that the two nodes of interest are this one and this one, then even though the two resistors are not drawn geometrically in parallel, they are still electrically in parallel. Right? So here's a node, here's another node, and they're connected in parallel because they're connected between those two same areas of constant voltage, those same two nodes. Conversely, just because two resistors are drawn geometrically in parallel, like here R1 and R3 are parallel geometrically, they're not connected in parallel electrically, because this node is different from this node. There's a potential voltage drop across R2, so unless R2 had a resistance of 0, R1 and R3 are not in parallel. And one thing I haven't shown here is, in the slides, is how to figure out what an equivalent single resistance is. So let me just go here. So if I have my two resistors in parallel, right, I have that resistor and I have that resistor. So that's R1 and that's R2, then I want to be able to convert that into a single total resistance, R total. Right? And the way I do that is for parallel resistances. The parallel resistance is 1 on R1 plus 1 on R2, like that. Okay, I should have put that in the slide, but it's okay, that's what it is. So when you can make this even more complicated. So for example, in this circuit we have three ohm resistors in parallel. We then have some those three ohm resistors are in series with the 5 ohm resistance. And that whole resistance, the combination of the 5 ohm and the 3 ohm resistance, is in parallel with 2 6 ohm resistors. And then that whole resistance is in series with the 5 ohm resistance. So using our parallel connections, total resistance, then the total resistance here is 1 on 3 plus 1 on 3 plus 1 on 3. So that's a total of 1 ohm for those resistances amalgamated together. 1 ohm plus 5 ohms in series gives us 6 ohms. Then we have 6 ohms, 6 ohms, 6 ohms all in parallel. So the resistance is 1 on 6 plus 1 on 6 plus 1 on 6, which is a total of 2 ohms. And then that 2 ohm total resistance is in series with a 5 ohm. So this circuit has a total resistance of 7 ohms. We could replace this entire circuit with a single 7 ohm resistor. So that's how we use series and parallel circuits to make simpler circuits. Another thing we need to talk about in this course is Kirchhoff's voltage law. Kirchhoff's voltage law says that the algebraic sum of the voltages around any loop in a circuit is identically 0 for all time. So what does that look like? So what that looks like is if I have a loop like this, right? Then the voltage drop across here, plus the voltage drop across here, plus the voltage drop across here. So let's call this V1, V2, and V3. And that Kirchhoff's voltage law says that V1 plus V2 plus V3 equals 0. If that didn't happen, if I could go around this loop and have the sum of the voltages be non-zero, then I could go around the loop again and get a multiple of that non-zero voltage, right? And I could effectively keep going around and get whatever voltage I wanted. So KVL, the way I'll usually write it, KVL, Kirchhoff's voltage law, says that. There's a very similar law.
Okay, so earlier I talked about the node. I used another word just then, which is loop, which we need to understand. And a loop is a closed path around a circuit that doesn't cross itself. And closed just means that it ends where it starts. Okay? There's another couple of things. One of them is branch and one of them is mesh, but I'll talk about those shortly, or maybe later in the course. Let's go back to the video.
Which is the next one on the list, called Kirchhoff's current law. Okay, Kirchhoff's current law says that the algebraic sum of the currents into a node at any instant is 0. So let's figure out what that says. Okay, we'll go back to our diagram. And what that says is if I have a node and I have several currents flowing into it. I have I1, I have I2, I have I3, and I have I4. Then what Kirchhoff's current law, KCL, says is I1 plus I2 plus I3 plus I4 equals 0. And again, if that didn't hold, if the sum of all these currents going into the node was not 0, then that would mean I could get current accumulation here. And I could effectively build up, again, power out of nothing. Okay. 2 more things I need to talk about in this slide deck. One of them is voltage dividers. Right? A voltage divider is where you have a voltage source and you have 2 resistors, and you want to figure out what the voltage drop across each of the resistors is. And in this case, the voltage drop across R2, the second resistor, is going to be the input voltage, which in this case is minus 15 volts. I'll talk about that shortly, times R2, which is 20 kilo ohms, divided by R1 plus R2. Right? So it's going to be 2/3 of minus 15 volts, which should be minus 10 volts. And then similarly for current sources, if you've got a current source and you've got parallel resistors, and you want to figure out the current through R2, this one's a little tricky because the current through R2 depends on the resistance in the other branch. So here IR2 is equal to 5 divided by 5 plus 10 times the input current being 3 milliamps. So it's going to be 5 divided by 15, which is 1/3 of 3 milliamps, which means IR2 will be 1 milliamp. Because of Kirchhoff's current law, we've got 3 milliamps going into the node, we've got 1 milliamp going through R2, so that means we also have to have 2 milliamps going through R1 in order for Kirchhoff's current law to be made true. Okay, that's all I have for topic 3.
Okay, so the things that were in that part of the video, right? Series, resistors, parallel resistors, Kirchhoff's voltage law, Kirchhoff's current law, voltage dividers, and current dividers. Let's just go back to our list of topics. Right, so we've talked about voltage and current and resistance and power and energy and series circuits and parallel circuits. didn't actually talk too much about combination, but effectively it's just being able to apply series circuits and parallel circuits after you've replaced the series or parallel circuits with its single equivalent resistance. We've talked about the passive sign convention. We've talked about Ohm's law. We've talked about Kirchhoff's voltage law. We've talked about Kirchhoff's current law. We've talked about resistance from resistivity and shape. We've talked about resistance change with temperature. We've talked about voltage dividers, and we've talked about current dividers. So we are ploughing through the topics in this course. Don't worry, we'll need to slow down a little bit shortly. We will need to slow down a little bit with mesh analysis and nodal analysis and superposition and Thevenin and some of the other topics. The reason why we're seem to be going so quickly so far is because most of what I've talked about, or the video has talked about tonight, is relatively straightforward. It's just fundamental, simple equations, right? You saw me do homework 1. You should be able to do that without too much trouble. You saw me do the lab mostly. You should be able to do that without too much trouble. The next homework is about dividers and KCL and KVL. That's not due for another 2 weeks, so you should be able to do it now. In fact, I know some of you have already attempted some of the questions there, so you should be able to do that. The difference between what we've talked about so far and the next things is the next thing, mesh analysis, nodal analysis, superposition, and Thevenin and Norton. These are now starting to be more algorithms. We could solve just about any circuit with all the stuff that we've talked about tonight. Any RLC circuit anyway. Resistor, inductor, and capacitor circuit. But it would be painful. What these algorithms, mesh analysis, nodal analysis, superposition, Thevenin and Norton, what they let us do is they let us systematize approaching complicated circuits. And because that systemization takes a while to get used to, we're going to have to slow down a little bit when doing those. The second list of topics on the right is pretty much exactly what we've done on the left. We're going to go through everything again. The difference being, instead of just having resistors in the circuit, we'll also have inductors and capacitors. And the reason why that's different is because instead of having real valued voltages, currents, and resistances, we'll have complex valued voltages, currents, and I'm going to call it an impedance rather than a resistance. But it's exactly the same stuff, exactly what we just did. Everything still applies, even though everything is complex. That is, you've got the square root of -1, the unit imaginary number coming into it. But we'll talk about that. That's a little way off yet. Any questions so far?
Could you explain the like the watt hours, watts, second, like that?
What?
Determine?
Yeah, they're a bit. Let me just pull that down. I'm just going to go back to. So there's a power brick. Let's call it a USB power brick. Maybe that's what they're called. USB battery pack, maybe. I should have. Right, so there's an example, a USB battery pack, right, a portable charger. And most portable chargers give their capacity in milliamp hours. And just about all of the early questions, homework questions and the tutorial questions are really about converting units. So if you keep the units in mind, that'll often be the best, right? So one of the sorts of units is, as I just said there, milliamp hours. But remember, we're trying to use SI units as much as possible. So that's going to be, right, 10 to the minus 3 amps. And then the hours we usually want to get into seconds. So there's 60 minutes in an hour and there's 60 seconds in a minute. Right, so to get to seconds, that's going to be 3600. Professor Broderick calls this these sorts of numbers milliamp hours, or the other one I think you mentioned was watt hours, right? He calls them, I think, stupid units of energy. Yeah. Right.
That's why I was like, this doesn't really explain it very much, but I kind of understand. I'm just trying to add them together to regular units.
Yeah, and it's just a matter of doing the appropriate unit conversions. That's all it is, right? Make sure you get, if you're asked to generate a watt hours number, make sure you've got to get to joules first and then joules per second, which gives you watts. And if you get your seconds, then you've got to multiply by 60 to get minutes and 60 again to get hours, or divide seconds by 60 and by 60 again to go from seconds to hours, and then you multiply the two numbers to get watt hours. Right? Whoever was in marketing that came up with milliamp hours and watt hours should be shot. But it is what it is, so we have to deal with it. But all it is just making sure you get the units right. And a lot of the stuff in engineering generally, not just electrical even, if you can get your units consistent, that goes a long way towards getting the right answer. Not always true, because you might have started off with the wrong number, right? But
that's generally how I double check. I guess you can call it.
Yeah. No,
So
it's a good habit to
guess
get into.
In this watt hours thing, so and again, I'm very unfamiliar with the electric or circuit equivalencies, but like a watt is joules per second. Is it equivalent to 1 joule per second?
Yeah.
Right.
Yeah. 1 watt.
So
1 watt.
then you can say, 1 watt equals 1 joule per second, and if you had the watt hour, you could say 1 joule per second with the converting in hours to 3600, so it'd be 3600 joules per second.
So what is it? You're saying 1 watt hour?
Yeah, would that be 3600 joules per second if that's the case?
Well, remember, this is a unit of power, and this is a unit of energy, right? So really, if you multiply this number, right, this is really 1 joule per second times hours, right? So it's 1 joule per second over an hour. So if you multiply it by 3600, which is seconds per hour, you're getting the energy, which is just joules, it's not watts. Okay.
Okay.
It's not,
Yep.
it's not joules per second. It's just total energy. It's not the energy per unit time.
Great.
Okay. You're welcome. Okay. Let's just have a look at the next video. Is about 21 minutes, and it's basically just about some background information on linear algebra and complex numbers. I'm happy to play that. I'm happy to talk about something else if you would rather me look at something else. Let me know what you want to do. Quickly. If you're okay, I'll just go with the video, and then we'll leave it there for the evening.
Where you've got usually a square matrix.
Sorry. Let's try that again.
Okay, so this is lecture 3 for CET236 on Saturdays. So for February 3rd, 2018. Please review this video before coming to class.
And again, complex numbers and linear algebra have not changed in, well, probably hundreds of years. So the fact that this is a 2018 video is neither here nor there.
During this class we're going to do a lab, which is only for the passive sign convention. We're going to discuss some of the stuff I'm talking about here and do some problem solving or tutorials using it. Also fill in a few more details during the class. There's one change from last week. One of the students pointed out to me that there's no class.
Sorry, I'm just going to skip forward. This
We'll
is
need to know how to
just
use a
stuff.
form. What's linear? We'll need to know how to use a power supply, so I'll give a bit of an introduction to that. Okay, so background, linear algebra. What's linear algebra? Linear algebra is expressing equations in matrix form, where you've got usually a square matrix multiplying a vector of unknowns equaling a vector of constants. So this is the form that we'll usually see it in this class, where you've got resistances, and in the square matrix you've got currents in the first vector, and you've got voltages in the vector on the right hand side. And one way to solve that is find what I1 and I2 is to pre-multiply everything by the inverse of the square matrix. And that's the way we'll try and get towards doing it. There's a couple of other methods of solving it, but your calculators should be good enough to do that inverse and do the matrix vector multiplication. So one way to do it without a calculator is to convert that equation into, or that matrix equation into two scalar equations in I1 and I2. And that's what's in the red and the blue there. And the method of elimination, which is the first method, manual method we could use, is to basically look at multiplying
one or both equations by some constant, so that the coefficient of either I1 or I2 equals the coefficient in the other equation, and then you subtract, so that that eliminates one of the variables. So in this instance, one way we could do it is to multiply equation 1 by 2. That'll make the I2 coefficient the same in both 2 times I1 and 2 times equation 1 and equation 2. And then we can subtract equation 2 from that. That gives us 36I1 equals 42. And that means that I1 is 1.1667 amps. And we can substitute that back into 1 to see that I2 is 0.5833 amps. It looks like I left out an amp sign there. Other way we could do it is pretty similar. It's called the method of substitution. And that's just to rearrange one of the equations so that you've got one variable, one unknown variable on one side and the other unknown variable on the other, relating the two. So we could rearrange equation 1 so that to get I1 equals, open parenthesis, 21 plus 24I2, close parenthesis, on 30. And we can then substitute that into equation 2 to get that, and then do a bit of rearranging. So eventually we get what I2 equals, which is 0.5833 amps, and substituting this back in yields I1. And funnily enough, the answers are the same. Now, we could do the same thing using a calculator. I'm not going to do it. I'm going to get you to do it during class, and we'll see if we can do that. I did use my daughter's calculator to do a short video about how to enter the matrix and do a matrix inverse. That's the YouTube link there. So have a look at that if you can't figure it out. And I think there's also a link to a web page that describes how to do it in Blackboard. So have a look at that. The other way we could do it is using MATLAB. And you can get onto MATLAB using the apps.ccsu.edu link there at the bottom left, and go to academic applications/MATLAB. And then you can just enter A, like the square matrix like you have on the left hand side there. I suppose it's a bit small to see in the video, but maybe the slides will make it more easy to see. Then get into B. And then there's a few ways you can do the inverse. One of them, the most numerically stable, is to, I think it's called a Cholesky factor, which is a backslash, not the normal division operator, but the one that slopes from left to right rather than right to left. The other way we could do it is to find the matrix inverse. That can have numerical problems. And a third way we could do it is to use the pseudo-inverse, which is more numerically stable than the inverse one, but not quite as good as the other one. Okay, that's about all I want to say about linear algebra. The other piece of background I wanted to talk about is imaginary numbers. So here we've got the right-hand side, we've got a graph showing the cosine of 0 is 1, and on the left-hand side we've got a two-dimensional representation. So our real value is in the along the x-axis, the RE axis as it's marked there, and we're at 0 degrees for the RE axis. And then we can rotate that vector a little bit by 45 degrees, and that the projection of that vector onto the RE axis, the x value of that, the end of that arrow, is now at 0.707. And when we get to 90 degrees, the projection is onto the RE axis, the x-axis is 0. You rotate by 180 degrees, now we're at -1 on the RE axis, and then we get to 270, we're at 0 again, and we finally get to 360, and we've got a complete cycle of our cosine wave. So the thing that's being plotted on the right-hand side there is just the real value of that vector spinning around the origin on the left-hand side. What we're really interested in is the actual position of that, the end of that arrow. So we've got to have a y ordinate as well as the x ordinate, the imaginary component instead of the real component. And basically complex numbers are just a way to work with two vectors instead of scalars. So in a lot of mechanics and statics, you may have gotten used to using the 3D vectors I hat, j hat, k hat. They're unit vectors. I hat is along the x-axis, j hat is along the y-axis, and k hat is along the z-axis. Now, a lot of mathematicians so the y-axis is a component that is going in what's the imaginary direction, and it's imaginary because it's in the direction of the square root of -1. Mathematicians use I for that. Unfortunately, in this course, we use I for current. So we're going to use J instead. And just to note, that I hat, J hat, and K hat image there is taken from Wikipedia, and it's available under the Creative Commons attribution, which means I have to give them credit for it, which I've just done, and the share alike license. Okay, so here's a few complex numbers. There's a blue one, a red one, and an orange one. The blue one is +3, there's no imaginary component. The red one is blue one's +2. The red one is -3, there's no imaginary component there. The orange one, that's a bit hard to say exactly what the numbers are. The real component's a bit over -2, and the imaginary component's a bit over +3. So there's a few ways we can write these down, right? We could just write the x and y coordinates of all of those, and that's what we call the rectangular coordinates. So we take the distance along the real or the horizontal or the x-axis, and the distance along the imaginary or vertical or y-axis, and write them as coordinates. That's one way we could do it. Another way we could write it down is we could take the magnitude of the vector and write the angle with respect to the positive x-axis, the positive real axis. And a third way we could write it is in exponential form, where we have the magnitude A and the angle theta, but rather than writing it in some shorthand form, we write it A e to the j theta. And turns out there's an identity called the Euler identity, which says that e to the j theta is equal to cos theta plus j sine theta. Okay, that's about all. I'm in the class. I've got a couple of tutorial questions, and we'll try that some of those out on both the linear algebra component of what I've just talked about and the complex number component. As far as this lecture and okay, I think the next part of this video is going to get into the next topic that I don't want to start to cover until next week. So I think we might leave it there unless anybody has any questions. So just a reminder, you don't have to show up for these. If you're happy to go through by yourselves, that's okay. I will be sending out weekly reminders of the videos you should watch, just like I did for this one, and what's due and when it's due. If you need to talk to me, feel free to message me on via text on Discord. That's probably the simplest way if it's quick. If it's not a quick answer, then I'll ask you to book a time with me on Tuesday, Wednesday or Thursday afternoons or evenings when it suits you. Any questions? Okay,